frequency domain plots. The same sine wave. Now look here. Figure A is a representation of a sine wave, and figure B is also a representation of a sine wave. Now look here, the amplitude in figure A is 5 volt, right? Getting the peak value is 5. Getting so you know the frequency in first figure A is about 6. There are 6 cycles. Okay, so that's why its frequency is 6 hertz, right? Now the same sine wave is represented using frequency domain plot. Now look here, how many frequencies are there? How many cycles are there? 6. 6. Now at 6 position here we have a spike. The spike is up to 5 because the 5 represents the amplitude. Getting? So the representation in figure B is a representation of the sine wave in figure A. Getting? So yeah, now look here. This is the representation in figure B is a complete representation of the entire sine wave here. How many cycles are there? 6, right? And the amplitude, look here, the amplitude 5. The peak value. What is the peak value of the sine wave? Maximum value 5. So that is represented using a single spike. Getting? So the advantage of frequency domain plotting is that we can see the values of frequency and peak amplitude easily. Okay, and number of frequencies. Number of sine waves can be represented using this frequency domain plot. Getting? So take one more example, or before that, this is the factor, or this is the note. So a complete sine wave in the time domain can be represented by one single spike in the frequency domain. As here you can see, there are many, there are amplitude. Look here, here high amplitude, here as well high amplitude. Okay, but here the entire amplitude, all peak values, is represented using a single spike with their maximum peak value. Getting? So now take one more example. Regarding the frequency domain. I hope you are getting frequency domain. So frequency domain plotting or frequency domain representation is more compact, and it is it's more compact, and because of this it is useful in dealing with number of sine waves, right? Okay, so for representing many sine waves we are using frequency domain plotting. Now take the example here. Now in this example we have 3 sine waves having different amplitude and different frequency, but the entire all these sine waves can be represented using frequency domain. Okay, frequency domain plot. Now look here. Now we have 3 sine waves here. 3 sine waves. One sine wave with the pink color, right? Another with green, and third one is this blue. A sine wave having color blue is having frequency 0. Its frequency is 0, because it's just simple horizontal line. right? But its amplitude, look at its amplitude. Its amplitude is 15, right? Whereas the amplitude of the sine wave is having green color, its amplitude is 5, and the amplitude of the sine wave in pink color is having 10. You know? Now look here, we have plotted these 3 sine waves in time domain in figure A. Okay. So these sine waves are having frequencies 0, 0 of blue, then 8, 8, no, not yes, 0 frequency of blue, then 8 frequency, 8 frequency of which? What is the okay? Which sine wave? So each sine wave is having frequency 8, pink, right? Look at here. 1. How many cycles are there? 1, 2, 3, 4, 5, 6, 7, and 8. 8 cycles are there. So its frequency is 8. And then green sine wave. How many frequencies are there for green sine wave? 16, right? So look at the representation in figure A and figure B. In figure B, we have plotted all frequencies, sorry, all sine waves. So the sine wave in blue is having frequency 0 and its amplitude is 15. Pink, 8 frequency and amplitude around 10. Then green having 16 frequency and 5 amplitude, right? Getting this? So we are talking about the time domain and frequency domain. Okay? So this plotting. So this plotting is useful for dealing with sine waves. Okay. So we can plot. You can either use time domain plot or frequency domain plot. But frequency domain plots are easy, as far as representation is concerned. Getting? Okay. Now the next point is this, that is signals and communication. So we know that the sine wave is the okay, it's a representation of a signal, right? But here this sine wave is not useful in data communication. A single sine wave is not useful. We know that a single sine wave is used in our houses for providing you electricity. So its frequency is around 60 hertz, right? Whereas sometimes you produce sine wave for okay, sending some signals to some alarm or say to your AC. So that also comprises a single sine wave. Getting? But the single sine wave is not useful in data communication. Getting? So for data communication, we need composite signal. A single sine wave is not enough. Okay. So composite signal consisting of many simple sine waves are required in data communication. Getting? So as far as the Fourier, a composite signal is a combination of simple sine waves with different frequencies, with different amplitudes and different phases. I hope you know Fourier. There is a great mathematician. Okay, so he has shown that the single sine wave is not enough for data communication. For data communication, we need composite signals, right? Getting? So a composite signal is nothing but it's a combination of different sine waves. Getting? Having different amplitude, different phase, or different frequency. So now let us discuss the composite signal. So as far as composite signals are concerned, composite signals can be periodic as well as non-periodic. I hope you remember what do you mean by periodic and non-periodic. So if we have a composite signal, if our signal is periodic, then its decomposition. I mean, when we decompose that signal, okay, we get a series of signal with discrete frequencies. Okay, and these signals are having frequency values in integers, right? And if the signal is non-periodic, then the decomposition of that signals gives the combination of infinite number of simple sine waves with continuous frequencies. Now, see, as far as the signals, digital signals are concerned, these digital signals are used obviously in data communication. Even a simple sine wave is also used for communication. But when we are talking about data communication, so for data communication, a simple sine wave or simple signal, okay, a simple analog signal, that is not enough. So we need a composite signal, right? So for composite signal, what do you mean by composite signal? A signal consisting of number of sine waves having different amplitude, frequency, or phase, etc. Getting? So when we say divide that or decompose that signal, composite signal, specifically the periodic signal, we get obviously some series of signals, okay, that have discrete frequency, and okay, and that frequencies are in some integer values, right? Getting? And if the composite signal is non-periodic, then the decomposition, remember here, look here, the decomposition gives us combination of infinite number of simple sine waves with continuous frequencies, right? Now here is a example. Now in this example, we show a periodic composite signal with frequency f, and so actually this type of signal is not typical of those signals that are found in data communication, but here we are just considering it for understanding how a composite signal gets decomposed, or how we have to decompose a signal, right? Getting? So here we have a composite signal okay, with different frequencies, right? Now here is that signal. Now here is a composite signals. Now here you can see a composite signal, as the name implies, composite. That means it's having a number of signals with different amplitude, different phase, or different frequencies, right? So obviously we have to decompose it. So how this gets decomposed? How this composite signal gets decomposed? Now here we are assuming that we have now we have three frequencies. Sorry, we have three sine waves. Okay, or sorry, in other words, now here this is our composite signals, and this composite signal is comprised or consists of these three sine waves. One sine wave, look here, one sine wave in pink is having frequency f. Another sine wave having frequency 3f and 9f. Getting? So remember, as far as the decomposition is concerned, decomposition is difficult. For I mean, decomposition. Suppose if we decide to decompose it manually, it's difficult, right? So but we have to decompose it. So for decomposition of signal is done by using some hardware or software, right? So that we are not going to discuss here, but say it's difficult, right? Now here we are considering that we have frequency. We have three frequencies. Okay, we have three sine waves with frequency f, another sine wave with frequency 3f, okay, and 9f. Getting? So these are the frequencies in the composite signal, and the frequency having, I mean, the first frequency in that pink color, okay, which is having frequency f. The sine wave, the sine wave having frequency f, okay, in the composite signal is called, okay, that may be what is that, fundamental frequency, or it's the first harmonic, okay, and the sine wave with frequency 3 has a frequency of 3 times the fundamental frequency, so it's called the third harmonic. And the third sine wave with frequency 9f has frequency of 9 times. So the fundamental frequency, I mean 9 times of the fundamental frequency. So it's called the ninth harmonic. Okay. Remember, the frequency decomposition of signal is discrete. So as we have discussed that it has frequencies 3f, 9f, and f, because f is an integer number. 3f, 9f are also integer numbers. There are no frequencies such as 1.2 or 2.6 or the frequency. Okay. The frequency domain of a periodic composite signal is always made of discrete spike. Now, if you look at the representation, the first representation of the composite signal, which is decompose. Okay, we have decomposed that signal. Remember, we have decomposed that signal and we have derived three frequencies, right? And that is plotted in time domain. Okay, and in frequency domain in figure B. So in frequency domain here we can see the frequency of, now here we are assuming that the frequency of sine wave in pink is f, blue 3f, and the black 9f. Okay, getting? So now actually, as far as this representation or this communication are concerned, these are the basics in communication. So I hope you might have studied this in second year, might be, I don't know. But this is a part of, I mean, communication. I mean, communication at low level. Our concern is data communication. Okay. For data communication we need the composite signal. Sine wave is not enough for data communication, so that's why we need composite signal. But see, when we are discussing the communication and we have composite signal, that composite signal is supposed to be decomposed, right? So how decomposition takes place? Decomposition is carried out using, say, so there are some hardware or software, so that we are not discussing here. Okay. Now some of you might be thinking that, okay, so now we have this composite signal, how to divide this? So we are not dividing this, and we are not interested in it, and that is not part of our study. Okay. Such composite signals are required for data communication. Such composite signals needs to be decomposed, right? And the the decomposed signals can be represented using such time domain plot or frequency domain plot. Getting? Now here is one more example. Now this is example is about non-periodic composite signal. So this non-periodic composite signal can be the result of a communication by using a microphone or telephone, right? So here, look here. Now this signal. Getting? So in figure B, so in figure A, we have represented the composite signal which is having which is non-periodic. Okay, using a time domain plot. So in a time domain representation of this signal, there are an infinite number of simple sine frequencies. Okay. Though the number of frequencies in human voices are infinite, the range is limited. Now, as I already told you, that this may be the result of a communication over telephone, or maybe communication over a telephone or some other device, audio device, right? So a normal, now this look at the representation. Representation is not continuous, because normal human being can continuous signal, continuous range. It can create frequencies up to certain range, right? So that signal is non-periodic signal is represented using a time domain and frequency domain here in this slide. Now let us discuss the next term, that is bandwidth and signal frequency. So as far as the bandwidth is concerned, what do you mean by bandwidth? We might we might be hearing this word bandwidth many times. So bandwidth is nothing but is the difference, obviously difference, between the highest and the lowest frequencies. bandwidth of a signal, and obviously we are interested in composite signal. So the bandwidth of a composite signal is the difference between the highest and the lowest frequencies contained in that signal. Okay. Now here we have a figure. Now in this figure, we can show the concept of bandwidth. Okay. The figure shows two composite signals, one periodic and other non-periodic. The bandwidth of the periodic signal contains all integer frequencies between 1000 and 5000, 1000, 1001, 1002, and so on. The bandwidth of the non-periodic signal has the same range, but the frequencies are continuous. Getting? So the band, look here in figure here, we are showing the bandwidth of a periodic signal, and in figure B we have the bandwidth of non-periodic signal. Getting? So now here is one example. In the example, now here we have a periodic signal, and this periodic signal is decomposed into 5 sine waves with frequencies of 100, 300, 500, 700, and 900 hertz. Okay. So we have been asked to find out the bandwidth, and we have to draw its spectrum, assuming all components having a maximum amplitude of 10 volt. So the left FH, let's suppose FH be the highest frequency, and this F1 with the FL, the lowest frequency, and be the bandwidth. Then bandwidth is equal to, we know the difference. Okay, so bandwidth will be the highest minus lowest, so that is 800, right? And the spectrum has only 5 spikes at 100, 300, 500, 700, and 900. Okay, so the look here, 5 spikes. Where are the spikes? At these frequencies. So the bandwidth is equal to highest minus lowest. Okay, getting? So we have been asked to calculate the bandwidth, and we have been asked to represent it. That's all. Getting? Now here is one more example. Now in this example, we have a periodic signal, and it has a bandwidth of 20 hertz, and the highest frequency is 60 hertz. What is the lowest frequency? And we have been asked to draw the spectrum. So I hope we can easily calculate the frequency and draw the spectrum. Right. So these such simple examples are there. Simple examples are just go through the example. Now the Fourier analysis. So that is our. I mean, whether this is included in our syllabus or not. Check Fourier analysis. I think Fourier analysis is not mentioned in the syllabus. Anyway, what will you do? I will just give the introduction of Fourier analysis. So before the discussion of the Fourier analysis, let us talk about the examination, your examination, midterm examination. Some people are asking me on WhatsApp or in other communication media. I think such people are not attending the classes. Okay, these people are not regular in the classes. Okay, some of you might be thinking that, okay, how do I know that these people are, okay, your attendance is being recorded. Okay, I'm not doing, I'm not taking it manually. Your software is recording the attendance. Who has attended the class, for how many minutes he was active. So everything is recorded. And okay, I'm not insisting you on attending the classes because you are I mean enough mature for I mean for this, enough mature to take decisions either to attend or not to attend, whether it is beneficial to me or not beneficial. That's up to you because you are professional. You are part of a professional course, or you're a student of a professional course, right? So it's up to you. Okay, there are many resources for learning. Okay, I'm not the only source. So you'll get everything related to any course over the internet, right? So it's up to you. But as far as the minimum criteria or class policies are concerned, sometimes attendance might be created. I mean, might be considered for. I mean, evaluating you. Or classes are required for knowing what is happening or what you are supposed to do in the class or in practical, right? So as far as the midterm examinations are concerned, okay, it's final. I mean, it's final that it's your midterm examinations are going to be offline. And but it's not sure when this examination will happen. I mean, whether that examination will happen as per schedule, as per our calendar, or maybe postponed, or maybe obviously maybe postponed, will never prepone. So syllabus for the examination will be the syllabus that is covered up to the examination and before before starting the midterm examination. Okay, so that is my policy.